little over 100 of them. And they're listed on that periodic chart that you get to bring to the quiz with you. Now, if you have a chunk of pure element, and if you magnify it really, really, really big until you see the basic particles that make it up, of course, if it's a pure element, all the particles will be the same that make it up, okay? And they will be atoms. And so it's appropriate to talk about what an atom looks like to start with, okay? And just as there are, I don't know, 110 different elements, so it is true then, it only follows that there are 110 different kinds of atoms, okay? There's gold atoms and iron atoms and hydrogen atoms, and they have these little symbols, some of which are obvious, some of which are not. Every nurse should know what that symbol means right there because it's sodium. It comes from the Latin word natrium for sodium. And of course, sodium ion causes high blood pressure. So that's why nurses should know what that looks like. If you have hypernatremia, you have high blood sodium. So that's the word that's tossed around. So that's elements. We'll expand on them in the next slide. Compounds are basically made up of two or more elements combined, okay? And they combine on the most elementary level, that is, atoms combine to form molecules. And molecules are denoted by little formulas or big formulas. If it's a little molecule, it'll have a little formula like that, okay? And this is the formula for water, and it has 3 atoms in it. 2 hydrogens connected to 1 oxygen. And that's carbon dioxide, and that has 2 oxygens hooked onto 1 carbon. And if it's a bigger molecule, it'll have a longer, more convoluted formula. But you see kind of how the formulas work then. Okay, next slide. And so here are a couple different ways of looking at an atom. There are 3 particles that make up atoms. Neutrons, protons, and electrons. Okay? The neutrons and the protons, and there are 2 general regions in an atom. There's the nucleus in the center and electrons around the outside. It used to be, people used to think it was like a little solar system, that the electrons orbited around the nucleus, kind of like we orbit around the sun, but it's really not that way. It's more like you got the nucleus in the center, and there's the so-called electron cloud. And nobody really knows what the electrons are doing in that electron cloud. And for this little discussion, we don't care. It's just that they're there. The electron cloud forms the margin of the atom. And the atom is roughly spherical. And so the outside of the electron cloud is the outside of the atom. Okay? So neutrons and protons in the nucleus, and these are great true-false questions, and electrons outside of that. And there's nothing in between. Okay? A lot of an atom is made up of dead space. Okay? And you don't want to think about this stuff too hard or it'll hurt your head. So next slide. So this is a little bit of information about protons, neutrons, and electrons. Protons and neutrons have a mass of 1 atomic mass unit. Okay? And that's just about the smallest amount of mass you can have. Not quite, but almost. And these atoms, the human brain really hasn't evolved to the point where it can wrap itself around atoms, the structure of the atom and the structure of molecules. We have all of these models that we use to help us try and visualize what it's really like, but no one's ever seen an atom per se, and we have models that work experimentally, but no one's ever seen an atom, and it'll be a long time before anybody ever does, or before anybody ever really is able to visualize what one really looks like, okay? But there's no doubt, but what these two particles have mass and electrons do not. Electrons are the most important particle in chemistry because my definition of chemical change is the movement of electrons from one place to another. We've talked about how an electric current is a movement of electrons through a conductor. Electrons have a charge. Charge is very important in nature. Okay, we not only consider the mass, but the charge. A proton has a charge of +1, which is the smallest amount of charge you can have. Okay, smallest amount of positive charge you can have. A neutron has no charge, and an electron has a charge of -1, which is the smallest amount of negative charge you can have. And anytime you see a number with no units, you should ask, well, shouldn't it have units? But really, there are units of charge, but not on a level this small. For some reason, no one puts a unit after that. It's just customary not to. So you should know that information about neutrons, protons, and electrons. Good, true, false questions. Okay, next slide, please. And so this periodic chart of elements, elements can exist in two different forms. Okay, and I haven't said anything about that yet. You look at that periodic chart and you get no clue about the fact that elements can exist in two different forms. So you can have iron, for instance. You can either have the neutral element iron or iron ion. Which one, do you recall which one is most important in biological systems?
Ions.
Ions, okay? Because ions are charged, and thus they are polar, and thus they dissolve in water. Neutral elements are recognizable as being usually either, not always, but usually either metals or gases. So you can recognize if you're looking at a metal, like gold, you're looking at the neutral element. There's such a thing as gold ion, okay? But everyone is fixated on the neutral element, and it's highly stable. That's why you find it in nature. Most metals are not found in nature as the neutral element. They're found as the ion. And so metal ores, like, are mined and have to be, somehow they have to be converted back to the neutral element to be useful if you want to use them as a metal. And that's what they do with aluminum. Something like 5% of the electric current in the state of Oregon is used in these aluminum plants to stick the electrons back on the ion to convert it to the neutral element. Okay? And because that's what we make, beer cans and soft drink cans and all kinds of other things. Rims for sports cars and all sorts of cool things are made out of aluminum. Okay? So the neutral element is useful in many ways, but ions are what we find so often in living systems because they dissolve in water. And a cell is just a bag of water, isn't it? Really. So next slide. So this is sort of a expanded periodic chart, and we get to look at some elements specifically, and there's a number up above and a number down below. The number up above is called the atomic number, and it tells you how many protons you have in the nucleus. Hydrogen is the simplest atom, and it has an atomic number of 1. It only has 1 proton in the nucleus, and that's what makes it hydrogen. It is the number of protons that determines what element you have. Okay? So, if you change the number, those guys back in medieval days that wanted to change lead to gold, you'd have to go into every single atom and change the number of protons in the nucleus. And let me tell you, atoms are so unthinkably small, you could never do that. Okay? Unless you have a linear accelerator. But there was a shortage of those back in medieval days. So, okay, and so if you have 6 protons in the nucleus, you are carbon, okay? And I see one with 6 over there. That has 7 though, that must be nitrogen. Okay, 1, 2, 3, 4, yeah.
Go to the left.
It's what?
Left. One to the left is carbon.
This one over here,
Yes.
okay, yeah, it's got 6. Yeah, I'm having trouble seeing the symbol in the center. I can see the number of electrons. So if you have the same number of electrons as you do protons, remember electrons are negatively charged and protons are positively charged. So for instance, if you've got a carbon atom and got 6 protons, that adds up to a +6, doesn't it? And if you've got 6 electrons around the outside, that adds up to -6. And so you were talking then about the neutral element. A neutral element is neutral by charge-wise. It has the same number of positives as negatives. And that's what makes it a neutral element. Is the neutral element carbon either a metal or a gas?
No.
No, it's this black powder, isn't it?
Mm-hmm.
Okay, that we use in gunpowder. So there are some exceptions. Sulfur, the neutral element sulfur, is a yellow powder that we also use in gunpowder. And so the neutral element has the same number of protons as electrons. If it's an ion, it doesn't have the same number of protons as electrons. So oxygen has 6 atomic number of 8. Okay, and that means it's got 8 protons in the nucleus. You can either have the neutral element oxygen, which is the gas that we breathe, okay, or you can have oxide ion. And oxygen gas loves to grab 2 electrons from other things to become oxide ion. And you've all heard of oxide. And oxide ion combines with lots of positive ions to become like iron oxide is rust. Okay, is iron ion and oxide ion. And the way you get rust is when oxygen gas takes away electrons from iron metal to the 2 neutral elements that are converted to ions. And the ionic substance has a totally different appearance, doesn't it? Iron oxide doesn't look anything like iron. So it's funny, it's made out of the same elements, but it's really, strictly speaking, a different substance. Okay, so ionic substances are different substances than their corresponding neutral elements. So don't get bogged down in that. Next slide, please. The identity of the element is determined by the number of protons, whether you're talking about the neutral element or the ion. Next slide. There's that again. So we can go on.
Do you want to go back?
Yeah,
Sorry.
my projectionist is getting confused.
We've never seen that before. Let's
It's
move
called Confuse the Projectionist.
on. So move on?
Yes, please. So neutral elements possess the same number of protons as electrons in the atom. Okay. Neutral elements you could recognize if you got one, if it's either a gas or a metal, but there are a couple of exceptions like sulfur powder and charcoal and stuff like that. If you write it without a charge on it, if you write it just like that, then it should be assumed that it's the neutral element that you're talking about. The neutral element, sodium, is quite an interesting stuff. It's a metal that you can cut with a butter knife, and it's highly explosive with water. It's kind of dangerous stuff. You never even want to get close to it or mess around with it because it explodes, a really nasty explosion with water. On the other hand, sodium ion is what's in salt. It's what gives you high blood pressure and tastes salty, and and there's a world of difference between the metal and the ion. And the way we know it's an ion is because of that charge. You could write a +1 there if you wanted to. That would be fine. or not. So, okay? And ions are different in appearance. They're crystalline solids. You can never have just a bottle of positive ions or a bottle full of negative ions. You gotta have positive and negative ions together, okay? There's a law in nature called the law of conservation of charge that says for every positive charge, there must be a negative charge nearby because opposite charges stabilize each other, okay? So you'll never find a bottle full of sodium ions. It'll always be sodium chloride or sodium oxide or sodium blah blah. There'll be some other negative ion with it, okay? So, next slide. In biological systems, the ion is what's important because they are being charged, they're polar. And polar things dissolve in water because water's polar and lights dissolve lights. So when we say we have an iron requirement, we're really leaving out a little bit of information. Do you think you satisfy your iron requirement by having a tablespoon of iron filings?
No.
No, that really won't do the trick, will it? It's gotta be iron, okay? And iron is totally different critter that dissolves in water, and it's iron ions that we have 4 of in hemoglobin molecule. And oxygen binds to iron when it's contained inside hemoglobin. So when we talk about vitamins and minerals, the minerals are always metal ions. And we have a requirement for certain metal ions like iron ion and others. Okay? We need a certain amount of sodium ion for our nervous systems to function correctly. Okay? Next slide, please. So, okay, we've talked about elements and the fact that elements come in 2 different forms. The basic particle, whether you're talking about a neutral element or an ion, you're still talking about atoms. You either have a neutral atom or an atom that's an ion. Okay? So if you write it without a charge, it's just going to be one symbol. If you write it with a charge, then it's the ion. Compounds are, the basic particle is a molecule. A molecule is 2 or more atoms connected by a chemical bond. Here's some simple ones. They get much more complex, like table sugar is C12H22O11. So that's an example of a more complicated one, but they get a lot more complicated than that too. Okay? There's almost an infinite number of compounds possible, and they're making new ones every year. They probably make 1 million new ones every year, I don't know. And there is a publication in German called Beilstein that takes up half of a science library anymore, that has all of the, and it has, the real bugger is that you have to update it every year, and it's really expensive. Because if you make 1 million new things every year, then you've got to update your Beilstein every year, which is probably 20 or 30 new volumes, big thick volumes that look like Bibles with real thin paper with small print, very expensive. And I wonder even where you could find, I wonder if there's one, I wonder if University of Oregon has a complete Beilstein. You'd have to have a pretty large room to contain it. And you'd have to have quite a bit of money. They might. Okay. I'm not so sure it's practical anymore. Not only that, but I bet you it's kind of like you guys should know about the PDR, the physician's desk reference. You can't put all the drugs in one thick book anymore. So they have it online. And I bet you that Beilstein is online anymore. And that you pay a fee for access to it. It's probably the way it works. You just couldn't cram it into a library. You used to take special know-how to even find something in Beilstein. So, anyway, enough of that. Got me off. It's all your fault. You got me off on a tangent. Next slide, please. So, ionic compounds have positive ions and negative ions. Here we have looks like, is that sodium chloride? Okay, so a sodium ion and a chloride ion, sodium is +1 and chloride is -1. And these ions combine in the smallest whole number ratio so that the charges equal, the positive charges equal the negative charges. Okay, so the sodium's +1 because you want the charge of the overall molecule. You can't have extra positive or negative charge hanging around because it won't have anything to stabilize it. So this is a real simple ionic compound, sodium chloride. They go together 1 to 1. Okay? And both of them are important in the body. We're looking at salt, basically. And both ions serve a function in the body as long as you don't have too many of them. So it's like so many things, everything in moderation. Next slide, please. So if you have an ionic crystal, like a little salt crystal, these ions stack like little cannonballs inside there, and they alternate so that every positive ion is surrounded by 6 negative ions, and you get a lot of stabilization that way. Okay, opposite charges stabilize each other. So that's what an ionic crystal would look like. It dissolves nicely in water, most of them do, because it turns out that water is so polar that it can stabilize. It has enough charge character to stabilize ions when they're dissolved in it. Next slide. So you can, this tells the charges on all the common ions, and we'll be interested in a number of them. For instance, like carbonate's an important ion, and bicarbonate's important, phosphate's important. You see some of these ions have more than one atom. They're actually molecules with the charge. They're called polyatomic ions. Sulfate, you've heard of that. Nitrate, you've heard of that. Okay, and potassium and calcium and iron ion are also, and sodium ion. And hydrogen ion, we'll see, is very important. So these ions combine to form, you can't just have a bottle full of positive ions or a bottle full of negative ions. The positive ions have to be surrounded by an equivalent amount of negative charge. So that determines what the so-called ionic formula is going to be like. I am asking you on the quiz next week, I think as I recall, to write, I give you the names and you write the ionic formula. So I'll give you like calcium carbonate, and you can make a copy of this and bring it with you with nothing written on it. Okay? And you write the formula for me then. And I'll do a couple of them on the board up here for you.
So we can have a copy of that one?
You can make a copy of that and bring it with you to the quiz, don't forget, or you'll be really mad at yourself. So you can have 2 things with you on the quiz next week. You can have that periodic table with nothing written on it, and this with nothing written on it.
The one we give in the slide.
The one that is included in the study guide. Okay, the study guide that says chemistry comes alive. Okay. The last page of that study guide is periodic chart. So tear it off and bring it with you. So next slide, please. Formulas for ionic compounds. This is just what I'm talking about. You always, by custom, you write the positive ion on the left, the negative ion on the right. And you use the smallest whole number ratio so that the charge is balanced. So what's my next slide? Here's some examples. Okay. Sodium chloride is obvious. They're +1 and -1. Let's look at over here. How did we come up with the formula for calcium carbonate? Well, if you look on your ion chart, calcium is +2 ion, and chloride is a -1 ion, so it's gonna take 2 chlorides to stabilize the +2 charge, isn't it? Okay, and so we write positive ion, you leave the charges out in the finished product, and so you write calcium and then you write chloride and you use a subscript to indicate how many you have. So we got 2 chlorides to go with every calcium, so that's the formula for calcium chloride. It gets a little harder when you have a 2 and a 3 situation. So let's look at that. Okay, aluminum. It's a +3 ion. Good job, David. And so if I combine that, that's an error. I did it wrong on the slide. Don't look at that. Because aluminum is +3 and phosphate is -3. So what happens? They go together 1 to 1. Okay? So the formula is just like this. Let's try it with calcium. So here's the formula for aluminum phosphate. My goodness. I think with someone with my background would not make that mistake. Anyway, so let's try calcium phosphate, okay? So that is a little more interesting. That's probably what I was thinking of.
How do you get the number that you're trying to?
The charge on the ion,
Yeah.
you look it on my table, that ion chart. You
That's
don't
a-
have it with you,
That
it's
one.
that. That's the one that you make a copy of that and bring it with you to the quiz,
Yeah, aluminum is not on
okay? Got it?
Okay, I was just making sure because I was
Yes,
totally lost. 'cause
That's right. Well, yeah, there's no way you could know it.
Mhm.
You gotta have your iron chart.
So you're only gonna ask us ones that are.
I'll only ask you ones that are on that chart. Okay? Yeah.
And which one, the one that she showed for?
What?
Yeah.
Okay, okay.
Yeah, that one.
Okay.
So that's the one you wanna make a copy of, and if there's any question about that, it's called some common ions. If you got any question about that, call me on the phone but try not to forget. Write it down, some common ions. And download that, print it out, and bring it with you with nothing written on it. Okay? Because armed with that, you can do any of these. So how about calcium phosphate? Well, now we got a little more interesting situation. How are we gonna handle that?
Math?
Well, you're gonna have to have two of the -3s
And 3 of the plus
and
2.
3 of the +2s. Okay, and so the formula for calcium phosphate, you get why we did that? Because you got +6 and -6. This adds up to -6, that adds up to +6. The pluses gotta equal the minuses, smallest whole number ratio. So don't write C6H4, that's not the smallest whole number ratio. So we write C3, CA3. Do we write it like this? There's PO4, then do I write a 2 after it?
Are you ready?
No.
Well, that doesn't look too good, does it? It looks like you got 42 oxygens. So if you have an ion that has more than one atom, and if you have more than one of those ions, you have to use parentheses. Okay? Because this tells you got 2 of everything inside there. And so that's, you see, ammonium ion is a +1 ion. And phosphate ion is a -3 ion, okay? And so it takes 3 ammoniums to go with 1 phosphate. You see how they got that bottom one up there? Okay. Can you see why the second one from the bottom is incorrect? Okay. They
Yeah,
should go
but
together
there's
1 to 1.
12, and there's
It should
only-
be AlPO4, period, no parentheses, AlPO4. What about, let's think of another one, what about aluminum sulfate? What's the charge on sulfate? Anyone know? Well, you go back to that and look, and the charge on sulfate is -2, so if you've got aluminum sulfate, what are you gonna have to do? Have 2 aluminums and 3 sulfates, okay? And so the formula is gonna be Al2SO4 3. And all these substances are common. You can buy them in big jars. And on the label, you would see aluminum sulfate, and then be this formula. And you'd pay a lot of money for it these days, probably. So,
I remember doing it with a table. I took chemistry, and it's a little bit more complicated than yours doing it.
What?
I remember taking chemistry, and I'm learning it in a different way, which is more complicated than that.
Oh, my way's always the
So
best way.
that's good.
Except when I do it wrong. So I dropped one of these suckers. What did I do with that?
Are we allowed to write the charge on the table?
The charge is on the table.
It's the column to the front side.
Can we use that table or the other table?
Use them both,
Both, okay.
the periodic chart and the common ions.
'Cause the
Use
periodic
them
chart
both.
Has the,
You can't tell what the charge on the ion is by looking at the periodic chart,
No?
no,
Oh, no, that's just on the ground,
Yeah.
never mind.
okay? So, got the idea? So you'll have a couple of those on the quiz next week, but not just a ton of them. Won't
Like, how
count
would you
much.
ask that? Like,
What?
Just as if it's right here. Right
I'll
the
say,
formula.
I'll give you the name, I'll say calcium sulfate, I'll write out the words,
Oh, keep going.
and you write the formula.
Yeah.
And it's easy if you got your ion chart. If you don't have your ion chart, you won't be able to do it, okay?
You dropped this one.
Huh?